Good morning, everybody. Thank you for coming to my defense today. Today, I'll be talking about GPS imaging of vertical land motion and earthquake coseismic displacements in the GPS mega network. I'll just make sure I can get ahead. There we go. So the research presented here uses the GPS imaging technique to identify and analyze geophysical signals related to vertical land motion and earthquake deformation recorded by the GPS mega network. And I'll unpack what this means in a minute, but first I want to give you the roadmap. So first I'll give you some background on the GPS mega network, show you what GPS data looks like if you're not familiar with it, and then talk about some of the things you can see with GPS imaging. Then we'll apply GPS imaging to investigate geodetic signals of vertical land motion in the Great Plains and the Pacific Northwest United States before stepping kind of out of vertical land motion and looking at how we can apply GPS imaging to earthquake deformation. So this map shows the GPS mega network in purple circles. It's an amalgamation of several hundred regional networks that of almost 21,000 GPS stations worldwide. And this map here shows that the GPS stations are not evenly distributed around the globe, but in general, they're located around plate boundaries and tectonically active areas. So each one of these dots, each one of these GPS stations records position data called a time series. So on the right here is an example of a GPS time series from station P042 in Wyoming. So position data recorded by continuous GPS stations can be processed into 24-hour position solutions. And those are little blue dots shown in east, north, and up components that make up the time series. So we can use this relation between position and time to estimate velocity, and then we can identify patterns in those velocities that can give us insight into geologic processes happening at that location. So in this case, we're going to use velocity trends from the up component time series to examine vertical land motion and to create a vertical velocity field, such as this one. So the motivation behind this work really stems from vertical land motion work that the Nevada Geodetic Lab has been doing for the past several years using a method called GPS imaging. And GPS imaging is an analysis technique that interpolates spatial-temporal patterns of movement between stations to create a velocity field of hostile motion. And some of that work is summarized in this image of part of North America vertical land motion built from GPS data. So throughout this talk, red is going to be uplift, blue is subsidence. And some notable signals shown in this figure include continental scale effects, such as glacial isostatic adjustment or post-glacial rebound in Canada, and the crust compensating for that GIA by flexing downward to the south, especially in northern latitudes, which is a process called forebulge collapse. It can also show areas of regional uplift, such as magmatism at the Three Sisters, Yellowstone, and Long Valley volcanic complexes. It can also show uplift from different parts of the earthquake cycle. So post-seismic relaxation in Nevada and Southern California from multiple approximately magnitude 7 earthquakes that happened in the past century, as well as interseismic strain accumulation along the Pacific Northwest coast, where the Cascadia subduction zone is. It can also show regional subsidence, such as that in the Gulf of Mexico, which is from aquifer depletion and oil and gas production, as well as aquifer depletion signals in the Great Valley of California. But the power of GPS imaging is that it can be used to discover previously unknown signals and investigate the cause of motion. And that brings me to the first chapter that I'm going to cover today, vertical land motion of the High Plains Aquifer region of the United States. So here we use GPS imaging to discover this uplift signal in the central United States, which generally speaking, this is a relatively stable part of the continent. But this signal is in contrast to the subsiding surrounding subsidence caused by that core bulge collapse signal. There's no known tectonic activity over magnitude 6.5, which is generally the threshold needed to generate detectable post-seismic relaxation. And there's no known magmatism in this area that could be attributed to some source of uplift. But this area does include the southern part of the High Plains Aquifer. So we wanted to investigate whether or not the aquifer could be the source of uplift. So just some background on the aquifer. It's the largest aquifer in the United States. And the groundwater is primarily stored in the Ogallala Formation, which is shown here in orange. It's comprised of tertiary alluvium and unconsolidated sediments. And this aquifer is a major source of groundwater for crop irrigation and for livestock. Lastly, it's an unconfined aquifer, meaning that it's at atmospheric pressure, so it's able to rise and fall without a loss of porosity. And that's kind of shown by this schematic here in the middle. Unconfined aquifer doesn't have that confining unit capping the reservoir. So, water level trends in the aquifer for the past 100 years or so have been on the decline. And that's illustrated fairly well by this figure to the right. The hottest colors show the greatest levels of decline, and areas in the southwestern corner and southwestern corner, Kansas and the Texas Panhandle have seen declines over 45 meters in some areas. Furthermore, a paper by Scanlon et al. Estimate the water volume loss in the High Plains Aquifer at a rate of around 5.7 cubic kilometers lost per year. And since 1950 through 2007, they estimated 330 cubic kilometers of water had been lost. So it's a lot of water being depleted from the aquifer. But despite the water table being classified as continuous throughout the aquifer, there is a difference between water levels in the northern part compared to the southern part of the aquifer. So this is the north, this is the south. In the north, there are some declines, but there are also some increases, and the majority of data kind of oscillate around zero, indicating that there's a net-zero effect. There's clear seasonal swings, kind of illustrated by these bumps here. And that shows us the effect of precipitation on water usage and recharge. Now, in the southern part of the aquifer, there are dominant losses over time, and there's very minimal seasonal fluctuation, which means that there's little precipitation effect on the groundwater use and a consistent anthropogenic reliance on groundwater resources. This suggests that aquifer depletion related to human use of the resource is that there's aquifer depletion related to human use of the resource. So, noticeably, areas of largest groundwater decline roughly correlate with the uplift signal. And this begs the question, is hydrological unloading causing Great Plains crustal uplift? So to help answer this question, we use several different data types to investigate vertical land motion of the Great Plains region and the relationship to the High Plains Aquifer. So we divide the High Plains Aquifer into northern and southern sections because their signals are very different. We compare them to trends and water equivalent height from GRACE data. We look at climate trends using Palmer Drought Severity Index data as an analog for wet and dry seasons, and we use well data as an indicator of the human impact on the aquifer. So this map here just kind of summarizes some of the different data sets we're using. These polygons here represent climate districts. Blue is north, red is south. And circles are GPS data, triangles are well data. And within the aquifer bounds are color coordinated to north or south. So we first use the GPS imaging technique to analyze vertical land motion of the High Plains Aquifer region. And the first step is we estimate velocities from GPS time series for each of the 379 GPS stations using MIDAS, which is our robust trend estimator for that estimates trends that are insensitive to the effects of outliers, seasonality, and undocumented steps. Next, we apply a weighted median spatial filter on a Delaunay triangulation. Outliers here are vertical rates uncorroborated by nearest stations, and they're often caused by deficiencies in station or monument design, very localized effects, or equipment problems. So an example is along the Kansas-Oklahoma border, the bright red ones surrounded by blue ones, and that goes away after median spatial filtering. But there's other stations that also are filtered. The next step is these velocities are interpolated to a grid using weighted median estimation to create the vertical velocity field. And unfortunately, there are some artifacts from this step that are associated with the non-homogeneous GPS station distribution. So they look like fingers or shards. An example up here, there's a couple of weird ones in the middle. But we can correct for this using a bootstrapping statistical analysis, iterating the image 20 times, taking the median value of the vertical rate at each pixel to create this final velocity field. So signals that are similar between these stations are enhanced by GPS imaging, and they may be ascribed to the spatially coherent movement of the solid Earth. So next, we solve for the four-bulge collapse signal using Peltier's I6GD model, shown here. So we subtract this from this one, and it gives us our final GPS imaging result corrected for GIA, which shows a maximum uplift signal of 1.7 millimeters per year with respect to the surrounding areas located near the Texas Panhandle, and that uplift signal now extends throughout most of the Southern High Plains Aquifer. So, to understand the hydrological impacts on VLM, we turn to Gravity Recovery and Climate Experiment, or GRACE data, which measures gravity perturbations, including those caused by the changing distribution of water mass on the Earth's surface, including perturbations caused by groundwater extraction. Now, this signal, or this figure, really emphasizes the difference between the northern and southern parts of the aquifer. The northern part shows an increase in water mass, the southern part shows decreasing water mass, and the area of greatest water mass loss is located around the Texas Panhandle region, which is also the region of greatest uplift and also the region of greatest groundwater decline. So we can use these Goddard Space Flight Center solutions to see a finer picture of mass loss of approximately 2 centimeters per year located around the Texas Panhandle. So each one of these squares is a mass con or a mass concentration. I've been kind of using it interchangeably, so sorry. It's important to know that these mass cons are defined to 1 degree, 1 arc degree, but these mass changes are highly correlated to the neighboring mass cons. So the next question we wanted to answer was whether this uplift could be related to seasonal hydrological signals in the region. And we use GPS imaging to identify amplitude and phase trends in GPS time series. So for the amplitude, there are regional oscillations in the Rocky Mountains, Dallas-Fort Worth metropolitan area, and notably in the northern High Plains Aquifer, 3.5 millimeters. The peak phase indicates the High Plains Aquifer is at the intersection of three distinct domains of seasonal load timing. And these three areas, shown by kind of that green, red adjacent colors, magenta and blue, respond to loads applied at different times with their peak phase 60 days out of position, or out of phase, sorry. So to the southwest in this green and red, peak phase is in late winter to early spring. East, the peak phase is in the end of summer to early fall. And then the northwest has the peak phase in late autumn. So these patterns of motion fit with the broader timing of hydrological loading domains across the continental United States. And they further support the seasonal deformation is explained by hydrological loading. So next, we wanted to take a deeper dive into signals specifically located in the High Plains Aquifer. For the Northern Aquifer, we gathered 28 GPS time series, 28 Grace Mask Hunt time series, and 16 PDSI time series for climate districts intersecting or within the High Plains Aquifer bounds before averaging them to see what the overall trends were. So for the Northern Aquifer, the PDSI data indicate that there are more frequent periods of extreme wetness, which is on this side of the zero line. There's cyclical water mass loss and recovery shown by Grace, with more periods of mass gain than mass loss. And then in general, GPS trend shows subsiding. For the Southern High Plains, we used 49 GPS time series, 30 Grace Mascon time series, and 12 PDSI time series for climate districts and stations within or intersecting with the High Plains Aquifer in the southern part. So in the south, the trends indicate there are more frequent periods of extreme drought, greater mass loss with little to no recovery, shown by Grace. And then the general trend shows uplift through 2014, and then general or gradual leveling afterwards. So it's important to note that that period 2011 through 2014 was a very intense drought period. So we use the PDSI for the southern section to delineate between early and late periods to see how GPS imaging responds during relatively wet versus relatively dry times. And we split the time series at the end of this drought because, with a couple short exceptions, the PDSI was negative for the majority of the early period, so we can classify it as dry. And similarly, because the PDSI in the late period is mostly positive, we can classify this as more wet. So how does this look with GPS imaging? Well, for the early period, which included that severe drought, which was at the time the most severe drought in Texas state history, the uplift is the highest, and it extends through a large portion of the High Plains Aquifer, most of the aquifer actually. Now in the later period, which is dominated by trends of wetter weather, the GPS imaging result as a whole is dominated by subsidence. But even during this time, that in the Texas Panhandle, that subsidence is at a lesser rate, or there's minor uplift signals still coming through. So if we focus on this southern part of the aquifer, we can build a model to show how unloading water might affect the vertical crustal motion. So we develop a very simplified unloading model using the load depth software and preliminary reference earth model FREM elastic structure to estimate the freshwater mass unloading rate needed to best match the observed uplift. So the observed uplift is here, just kind of zoomed in. This is our model. So the perimeter of mass change, unload, is based on the region of vertical velocities here, with a rate of 1 millimeter per year or greater. And this perimeter was simplified to minimize the effects of bootstrapping here. So then we solved for water load thickness that minimizes the misfit between the observed uplift rate here and the uplift rate predicted by the model here. And that gives us this result, the residual. So even though the spatial distribution of this water loss is greatly simplified, our model shows that a loss rate of 11.4 centimeters per year, centralized in the Texas Panhandle region, is sufficient to approximate the uplift signal shown by GPS imaging. That's equivalent to about 5.1 cubic kilometers of water loss per year, centered just in this one polygon. So if we compare our estimated rates to GRACE, the unloading model maximum water equivalent height result of 11.4 centimeters per year is significantly higher than the 2.6 centimeters per year shown by GRACE. But if we compare our volume estimations from GRACE to the full GRACE model for the southern part of the High Plains Aquifer, it does significantly better. So we have 5.1 cubic kilometers. This estimates approximately 6.7 cubic kilometers of water loss. Now, finally, that Scanlon paper I mentioned earlier had a rate of minus 5.7 cubic kilometers per year. And that was between 1950 and 2007, so it overlaps our time frame. So we think this model is probably a good lower end estimate of average water loss in the region. So what is causing the differences? So the differences might be caused by the total water volume losses. It's centered on that simplified polygon. It's not perfect. It could be that the spatial resolution between GPS imaging and GRACE is different, and that's causing some uncertainty. It could be GRACE or GPS imaging is detecting changes in groundwater storage before the GRACE timeframe, or it could be GRACE underestimated the water volume loss or volume water loss. So, in summary, GPS imaging shows an uplift trend in the southern High Plains Aquifer. It's spatially connected to 8 areas of greatest groundwater withdrawal. GRACE shows that mass unloading in the southern High Plains Aquifer is consistent with a hydrologic source. That uplift correlates with periods and locations of drought, including an increased rate of uplift during extreme droughts in North Texas. The simplified mass unloading model indicates that a loss of water volume of 5.1 cubic kilometers per year can create that uplift uplift field shown by GPS imaging. An aquifer-controlled uplift suggests an anthropogenic source from groundwater depletion in the southern High Plains Aquifer. So is hydrological unloading causing High Plains crustal uplift? Yes, uplift is consistent with seasonal and anthropogenic-driven hydrological unloading, further aggravated by climate change. So GPS imaging helped identify the source of uplift, we think. So how can we apply it to other, maybe more geologically complex regions that might have overlapping signals? That brings us to the next chapter. Cascade arc subsidence in the Pacific Northwest. So the Pacific Northwest is a geologically complex area. It's home to the Cascadia subduction zone. It has a long history of plate subduction, a lot of classic features, and some of those are shown on this overview map. Here's the Cascadia subduction zone offshore, where the Juan de Fuca plate is subsiding beneath the North American plate. There's a Cascade volcanic arc that's had multiple recent eruptions and magmatic uplift, as I showed earlier. And then because it's, a subduction zone like this, it gets really large megathrust earthquakes. And there's interseismic strain accumulation along the coast, as I showed you earlier as well. Not only that, but it's in those northern latitudes. So parts of this area were covered by the Western Cordilleran ice sheets. So it's probably experiencing that forebulge collapse after that deglaciation. Not only that, but it's located along the coast this time. And that means there might be greater hydrological signals in a wetter climate that could be causing a hydrological loading. So here we ask, can we identify the source of subsidence here? with GPS imaging. And unfortunately, I do not have enough time to tell you everything I've done for this chapter, but I will give you some highlights, which are going to focus mostly on GIA and the megathrust event from 1700. So we're just going to jump right into it. Here's the GPS imaging analysis steps. Midas velocities are estimated for the 479 GPS stations in this region. These get median spatial filtered and then interpolated. That interpolation undergoes that artifact reduction, bootstrapping step. And then for good measure, hopefully it's not too small, I overlaid that vertical land motion on top of topography. See if there's any trends. And this kind of what's out there, but it kind of seems to follow the cascade arc, not surprisingly. So GPS imaging appeared to be showing the greatest amount of subsidence along the cascade arc and back arc, but just to check, I made some velocity profiles plotted across latitude transects, 48.5, 46.5, 44.5, 42.5 degrees latitude. So the blue here for these figures shows topography. The orange shows the GPS imaging result. The red shows the Midas velocities along the longitude. And then I added some geographic features that just for reference. And for each of these, there's an additional 20 kilometers of padding around the center latitude transects, just to illustrate a wider range of trends. So what these profiles really confirm is that the greatest amount of subsidence here, 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 and here roughly correspond to the location of the cascade arc. But before we can look at signals for the cascades, we have to correct this region for GIA. And we do the correction the same way we did using Peltier's I6GD model. This gets subtracted from our GPS imaging results here. And it shows that subsidence feature, although at a lesser rate, is still concentrated along the cascade arc, but the surrounding region is now showing uplift. That's clearly contrasting that subsidence signal. So now we look at possible sources of subsidence caused by that Cascadia subduction zone. And we do this using methods by Young et al. For the Pollitt's Coseismic model for the 1700 magnitude 9.1 Cascadia earthquake Coseismic. And using the estimated response at each of these GPS stations, we can construct a vertical velocity field using GPS imaging to correct our GPS imaging result that has GIA removed to find the final field. So here is the GIA corrected, post-seismic corrected vertical land motion field. And you can probably tell, but most of that subsidence feature is removed. So this really indicates that post-seismic in combination with the GIA response is probably the main source for the subsidence signal. So GPS imaging showed us minus 2 millimeters per year of subsiding, corresponding to cascade arc and longitude and cascade subduction zone latitudes. The GIA modeling of that four-bulge collapse after Western Cordilleran deglaciation accounted for some of that downward signal, but not along the cascade arc. So we brought in that post-seismic model for that 1700 magnitude 9.1 event. That accounted for most of the rest of it. So can we identify the source of subsidence? Well, if you combine the two, they're likely the main contributors to that subsidence feature. So this earthquake from 300 plus years ago is still deforming the Earth's crust to this day. And we could see how it affects vertical land motion with GPS imaging. Now, if an earthquake from that long ago can still make that much of an impact, it makes a really compelling argument for how important it is to be able to estimate how much the Earth moves from earthquake events in this modern era with GPS. So next, we're going to pivot a little away from post-seismic earthquake deformation to talk about coseismic displacements. So when I say coseismic displacement, I'm really talking about earthquakes, and this is a map of all of the earthquakes magnitude 5.5 or greater, recorded by the USGS National Earthquake Information Center between January 1st, 1994 and April 20th, 2022. We start at 1994 because that's the beginning of the NGL's data holdings for GPS data. So here there are 14,059 earthquakes included. The largest earthquakes tied at magnitude 9.1 for the 2004 Great Sumatra Andaman and the 2011 Great Tohoku Oki earthquakes. So what is a coseismic displacement? A coseismic displacement is a sharp, immediate discontinuity in the GPS time series caused by earthquake deformation near the GPS station. And to the left is an example GPS time series taken from station CCCC near Ridgecrest, California. These teal lines are equipment changes, and these gray lines are possible earthquake events. And in 2019, you could see that the east component drops down, the north component jumps up, the up component also jumps up. And this is the magnitude 7.1 Ridgecrest earthquake on GPS. So why does this matter? Well, for those interested in earthquake science, these coseismic displacements can provide information on the type of deformation from the event, as well as help seismologists resolve ambiguities in the source plane. But other researchers might be interested in longer-term signals. And coseismic displacements can impact estimations of velocity, strain, and more if they're not accounted for. So for either purpose, we need to be able to accurately estimate how large the coseismic displacement is at a given station. So to the right here is an example of a GPS station with many displacements. It's J037 near Sendai, Japan. This large step here is the Great Tohoku earthquake, but there are also several additional displacements that can give further details about ongoing coseismic, for example. So we need to be able to know the size of the displacement when working with data affected by an earthquake, no matter the purpose. So here I ask, how has the GPS mega network evolved in its ability to detect and characterize earthquakes over time? And this means answering questions about how the GPS mega network automatically decides which stations are affected by an earthquake and how it estimates the size of the coseismic displacement for an individual time series. And again, there's more work here than I have time to talk about, but I will focus on recent improvements to displacement estimation strategies before looking at other results. So the GPS mega network automatically decides which stations are potentially affected by an earthquake event using this equation for radius of influence shown by the solid circle on this image. And the radius of influence depends on the earthquake magnitude, and stations within this radius may have experienced coseismic displacement, but if they're, for example, far enough away, they may not have experienced any coseismic displacement. So this figure to the right here shows GPS imaging result of horizontal movement for the 2019 Ridgecrest earthquake. It has the radius of influence, and then this is the boundary of all stations used to make this GPS image. Now, where there are stations to constrain the GPS imaging result, the radius of influence captures these yellow-orange colors where coseismic displacement is the greatest. And this image was used by inputting horizontal displacement magnitudes instead of vertical velocities. So, So how are these coseismic displacements estimated? Well, there are two basic models for estimating coseismic displacements. The first is the time series model, with examples shown on the far left, and then the data near event model in the middle. These are coseismic displacements for the magnitude 6.5 Monte Cristo Range earthquake. And it might be a little hard to see on the screen, but the outside ring is the horizontal magnitude of the displacement. The inner ring is the uncertainty. So the current practice by the NGL is to use the time series model. And this solves for a velocity term in the time series using the Midas algorithm. And then it solves for remaining terms, seasonal, post-seismic, the earthquake displacements, and equipment changes, if there are any. So this time series model is what is shown by the red line in previous figures. I forgot to point it out. But that is what's currently being used in the lab. This data near event method uses position data within 30 days before and 30 days after the earthquake to estimate displacements. And this is what I worked on for part of my time here. So this new strategy infers both a trend and a coseismic displacement based on medians and Filson statistics similar to the Midas algorithm. So this data close in time to the event, using just that small window, results in less bias associated with unmodeled signals from seasonal, post-seismic, undocumented equipment changes, other earthquakes, hydrological deformation, for example. And you can kind of see the difference between these vector plots shown on the bottom. The data near event model has less scatter than the TSM model, which has these outliers near the periphery of the radius of influence. So this kind of brings us towards maybe implementing a displacement estimation hierarchy. If we have data for that 60-day period around an earthquake, we could use that 24-hour data near event estimation strategy. If there are earthquakes within that time, that window would get truncated. If there's not a full day afterwards, maybe there's an aftershock, for example, we can use 5-minute time series to estimate the D&E displacements. And otherwise, we could still use the time series model. So now that we have a way to estimate coseismic displacements, we can apply this strategy to the whole world, the whole GPS mega network. So here's the global map again with the GPS mega network, but this time I've also plotted stations flagged for earthquake displacements in gold. So there are 7,486 unique GPS stations plotted. That's 37% of the GPS mega network. And this accounts for over 63,000 possible earthquake displacements. So of the 14,059 earthquakes that occurred magnitude 5.5 or greater, 3,451 earthquakes were detected by at least one GPS station in the mega network, which is approximately 24.5% of the catalog. But if you look where a lot of the missing station or the missing undetectable earthquakes are, they align with those mid-oceanic ridges where there's no GPS instrumentation. And those are all smaller magnitude earthquakes. So it's not necessarily going to reach shore where the GPS stations are. And if you're curious how the mega network detects earthquakes only originating onshore, that number improves to 29%. We can take a closer look at some of the numbers. The top here is a breakdown of earthquakes seen by the GPS mega network compared to the NEIC catalog as far as percent detection goes. So the gray is onshore earthquakes, the black is total earthquakes. So again, onshore earthquakes do slightly better. But more importantly, earthquakes over magnitude 7.5 do a lot better. And by 8, everything is detected. On the bottom, we're showing catalog comparison by magnitude per year. So as the GPS network grows, there's an improvement as far as percent detected. The lower magnitude earthquakes, which occur along mid-oceanic ridges for the most part, are not doing so well, but those higher magnitude earthquakes are significantly better detected by the GPS mega network. So here I introduce you to the Nevada Geodetic Lab's Coseismic Displacement Estimation Strategy for the GPS mega network, including the data near event model, which improves the accuracy of coseismic displacement estimations in GPS time series. We then applied these strategies to the entirety of the GPS mega network to assess how it's done over time to detect earthquakes. And that shows us that 63,000 instances, where 7,486 unique GPS stations were able to detect an earthquake and estimate coseismic displacement. That number, 24.5%, is all the earthquakes that have been detected since January 1st, 1994. It improves for onshore earthquakes. So how has it done? Well, earthquake detection improves with time, increasing magnitude and onshore epicenter, which is not surprising. But for the stations that do capture earthquake deformation, we now have a better strategy for estimating coseismic displacement. So it's really a twofold improvement. So the goal of this dissertation was to investigate geodetic signals, or was to use GPS imaging to investigate geodetic signals. First, we looked at vertical land motion, uplift in the Great Plains. We used GPS imaging to reveal that seasonal and anthropogenic-driven hydrological unloading, further aggravated by climate change, is causing crustal uplifts. Next, we looked at a subsidence feature in the Pacific Northwest and determined that forebulge collapse from deglaciation to the north and post-seismic relaxation from the 1700 Cascadia earthquake are the primary sources for that subsidence feature of interest. And then finally, we took a step out. We looked how we could apply GPS imaging to earthquake deformation, and we discovered that GPS network has improved in its ability to detect and characterize earthquakes over time because of GPS network growth and also because of improved seismic displacement estimation. So, and with that, I'd just like to thank all the agencies and organizations that supported this research, but more importantly, the people that supported me. Thank you so much for all your help and camaraderie over the last 7 years that I've worked on this research. It has been a hell of a journey. Especially want to thank my advisor, Bill, and my committee members, Jeff, Courtney, Anna, John, of course, different professors I've had, mentors, fellow grad students, and thank you. And finally, my friends and family and my wonderful husband, Colin, in the back. I could not have gotten this far without all of your love and support. So thank you, and I'll be happy to take any questions.